My name is Alex Lee. This is my Physics 2211 Lab 3. Alright, so here's the introduction of the lab. So the purpose is to find the mass of the black hole by analyzing a star's motion and determine the initial velocity the ship must have when it leaves the surface of the planet to avoid crashing on the planet or the black hole. So here are some principles that we use. So we use Newton's second law, which relates to the interaction between systems and surroundings to the motion of the system. We use Newton's law of universal gravitation, which is the attraction non-constant force between two objects with mass. And the equations are listed to the side right there. And then here are some other formulas that I have used. So this is the force formula, which is force equals to gravity times big M times little m over r squared. And I also use F equals mv squared r, which is for F net perpendicular. And I also use that R equals R system minus R source. And then here are some fundamental equations. So F net equals F parallel plus F perpendicular. And then there's F net equals your change in momentum over your change in time. And then there's P equals mv. And then there's the position update formula and the velocity update formula. So here are my initial conditions for coding. And then here are the other ones. And so the result is the mass of the black hole is 3.03 times 10 to the 34 kilograms. I got my F net to be 9.767 times 10 to the 24 newtons. F net parallel equals 3.55 times 10 to the 28 newtons. F net perpendicular equals 9.1 times 10 to the 29 newtons. So what does this mean? And so this discusses how the net force and its parallel and perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components. So this is part 2 of my goal script. So our goal here is to find the initial velocity of a spaceship to help it make a figure-8 orbit. This is my initial conditions. And this is my result. So overall, pretty close. We didn't make it to the figure-8, but we got pretty close. So here are some possible errors. So maybe I did some rounding errors were not made for each iteration. This is a simulated calculation. Oops, so it's not exactly like how it would happen in reality. So there is bound to be a mismatch. And then accuracy was affected because it was a trial and error method. And then that we used to find the orbit track. Better velocity could have been chosen to be more specific to the lab. So part 2 was a lot of guessing and checking. So for the discussion, so what does this mean? The net force on the spaceship is determined by the gravitational attraction of both the planet and the moon. The net force on the moon is determined by the gravitational force from the planet, and this present influence of the spaceship. And the parallel component of the force to the velocity direction influences the rate of change of the magnitude of momentum. And the perpendicular component of the force changes the direction of momentum without changing its magnitude, leading to curved motion. So here is what if. So the black hole exerts a gravitational pull on all objects in the system. The star's gravity influences the planet and the moon, but is less dominant than the black hole's pull, and the planet has the largest influence over the moon due to their proximity. The black hole exerts the most significant force due to its giant mass, potentially destabilizing the orbit of the planet and the moon. The star's gravitational influence on the planet and moon will determine their long-term stability in orbit. The mass of each component and the distance between them will determine the motion of the system. So in conclusion, so through coding simulations, we were able to find the mass of a black hole. And then let's go back. So here, we did find the mass of the black hole. And then for part 2, we got relatively close to figure 8, but not exactly. All right. Thank you guys for listening.